Hi everyone, my name is David Pacheco. This is Brendan Gregg. We both work at Joyent on a project we call Cloud Analytics. We both worked at Sun Microsystems together previous to working at Joyent. We worked on the Fishworks team. And you may also know Brendan from his work on the DTrace book, which he co-authored, and the DTrace toolkit, which he also authored, and many other performance tools and books. We're now working at Joyent. For those who don't know, Joyent is a cloud company. We run one of the largest infrastructure as a service clouds in the world. I believe it's the third largest. And the project we're working on and that we're talking about today is called Cloud Analytics, which is a distributed system for visualizing performance of software deployed in that cloud. So Brendan's going to start off talking a little bit about the problem, then I'll talk a little bit more about how we actually went and solved this, and then we'll do a live demo and share some of our concluding thoughts.
So good day, my name is Brendan, as Dave said. And the way we work at Joyent, Dave works on more engineering and I'm more customer facing. So I have a good understanding of the problem that we're attacking because I work on performance escalations in the cloud. So the problem, we've deployed our software and performance sucks. That's standard. How do we figure out why? Latency is a key metric that we're focused on for cloud applications. And this is different from many traditional styles of performance monitoring, which are resource-based, which serve well for system administrators and operators. Latency is great for applications. So by measuring latency as a synchronous component of an application request, you're able to see the actual pain that a client felt when making a request to the application. So that's how long an operation takes while a client is waiting for data and while the user is waiting for a page to load. Latency, and there are a lot of performance monitoring tools out there, but latency hasn't been a focus for many of them. Some of them take existing system metrics and display them in some very neat ways. What we've done is we've shifted focus to latency, particularly for the application developers and support staff. So being able to measure latency, the problem is how do you summarize the latency of thousands of operations without losing important details? So the sort of performance escalations I work on involve latency for this database is very high. We have some outliers that have a full second of latency, or we have latency to this Apache server is very high. And averaging latency doesn't work so well, and I'll go into some screenshots to emphasize that. How do you summarize that across a distributed system? This is even more important for the cloud environment because applications can be distributed on 1,000 nodes, and you're trying to understand latency across all of them. And you have a complicated environment, which may have Apache, MySQL, Memcached, Zeus, load balancing. And how do you do this in real time? So a lot of these applications are very hot. They're production systems, and we want to be able to pinpoint the origin of latency as quick as possible. So that's the key points about the problem we have. It's about latency because we're focused on application developers. We want to summarize the information from all sorts of different locations, doing it across a distributed system, and then doing that in real time. So to understand latency a bit more, there are a few ways you can get access to latency data. One way is to trace or dump each event one by one, and then to post-process it. And there are quite a lot of tools out there. People get very good at post-processing trace dumps. This is a tool I wrote called IOSNOOP. IOSNOOP is actually by default on Mac OS X now. It prints out disk latency one by one. That's great because you're not losing any information. I've got latency measurements here. It's not very practical in a cloud environment. In fact, it's not really practical on a local system anymore if you're doing thousands of disk operations per second. This is great as a last resort when you have an event that you just can't understand and you actually need to step through details one by one. And apply this approach for anything in cloud computing. It might be connections to a database, it might be connections to Apache. I've done this in lots of locations where sometimes you do need to go through one by one the latency data. But most of the time this is a giant amount of data to process. So line graphs are great at summarizing that data so you don't have hundreds of screens of output to read. And they're good for, obviously they're good for identifying patterns over time. So this line graph is average latency, and I can see there is some sort of spike every 5 or 10 seconds. Line graphs, you have to think carefully about the metric here. This is average latency for those operations per second. So all of the events that happen in 1 second, we take their average. Why 1 second? It's just a convenient thing to plot. Some difficulties with this, outliers are hidden. So many of the performance escalations I'm working on, it's because your database has had a 1 second slow query and you need to know the details about it. However, that database is doing, the hot ones I'm working on are doing between 5 and 10,000 queries a second. If you just have one slow query and you're looking at the average latency, that's 0.1% of the average. So that's why people plot the average and the max to try and allow you to identify that. But there's actually more information there that you might want to know about without getting into standard deviations. Understanding the full distribution of latency is interesting beyond just 2 lines, beyond just an average and a max. So that's where we bring in heat maps. So for the heat map, and I used this previously when I worked at Sun Microsystems. We did this as for a storage product, Sun Storage Series, where we're plotting time on the x-axis, and you'll see this from the demos as it ticks along. On the y-axis, we have latency of the events. And instead of giving you an average or a maximum, for every I/O operation that happens in a particular time and latency range, we darken that pixel. So you can see where the average is, because that's where most of them are grouped. You can see outliers, because they're at the top of the plot. And you can also see other fascinating details that you just don't see with lines and with averages and maximums. This graph that I've got here comes from a MySQL database, a live MySQL database that's serving a very popular Facebook game. And even though we had a lot of staff working on performance, no one knew that you actually have this bimodal pattern of latency. In fact, if you look closely, there's actually 10 milliseconds. There are these 10 millisecond echoes of latency inside that graph. That's really, really interesting and pretty, but if that's all I give you, that's about as far as it gets. What we're doing in Joyent is we're adding a 4th dimension to heat maps. So the data that we're collecting for this contains not just the time and the latency and the number of operations, which is the darkness of the pixel. It also contains another dimension to help us analyze what that pattern is, or what originates that pattern. This is tables. So this is the same MySQL database that's doing a popular Facebook game, and it's the tables that have different latency. So one's down here, one's up here, and you can see there's another with those 10 millisecond echoes. Really, really fascinating stuff. This is particularly important because, as I said earlier, latency is what matters. That's time spent waiting. The higher it is, the worse it is. Unlike picking through many other metrics, especially IOP counts and throughput, which require some degree of interpretation, with latency it actually gets pretty simple. The higher it is, the worse it is. So you want to be able to pick on the high latency guys and then have some other dimension to analyze it and drill down further. So that's what we're doing with Joyent. And the problem I gave Dave to work on engineering is I want that heat map, but for all sorts of different areas. MySQL, Apache, the kernel, and so on. And back to Dave.
So Brendan's just explained the problem and where we want to go. We want heat maps that explain performance of software in the cloud. Then the question is, well, how do we go build such a system? And that's what I'm going to talk about next, and then we'll demo it. The first thing I want to start with are a couple of building blocks that have been enabling technologies for us. That's DTrace, OS-level virtualization, and Node.js. So I'll start off with DTrace. How many people here have actually heard of DTrace before? Yeah, that's pretty good. How many people have actually used it? Oh, that's awesome. Sweet. So for those who don't know, DTrace is a dynamic tracing facility. It was developed for Solaris several years ago and open sourced in 2005 with the rest of Solaris. So it's available on Solaris-derived operating systems, including the Lumos fork, as well as SmartOS, which is Joyent's operating system that's based on Lumos. It's been ported to Mac OS X and FreeBSD. We could spend an entire talk on just DTrace, so what I want to focus on right now is a couple of key aspects. DTrace is designed for absolutely safe instrumentation of production systems for performance analysis, among other things. It can also be used for debugging during development and such. But the important thing here is that it's absolutely safe. You can walk up to a production system and start tracing things using DTrace with no fear of bringing the system down or making things worse. And because it's designed for production, it doesn't require you to, say, restart applications with some debug flag or have a special debug kernel or something like that. This is designed for our production use. And it has zero disabled probe effect, which means when DTrace is not active, there's no cost. The system is running at full speed. And it has minimally invasive enabled probe effect. So the way DTrace, the model that DTrace presents is there's some number of probes on the system. On my MacBook, I checked earlier today, there are about 60,000 probes built into Mac OS X. That includes every function entry and exit point, every function entry and exit point inside the kernel. It also includes higher level semantic operations like an IO operation has been queued to disk, there's a probe for that. The scheduler has enqueued a thread on a dispatcher queue. The scheduler has put a thread on CPU, etc. There are these high level events. You can also go into user land, so you can trace every instruction and every function entry and exit in any process. Those are dynamic probes, so that wouldn't be included in the tens of thousands that are listed by default, but you can create as many as there are instructions in any process. In this particular example, this is a query that resembles the one that Brendan showed you a heat map for a few minutes ago. I'm sorry the code is a little bit small, it's kind of want to fit, but what we have here is a DTrace script which enables two probes, MySQL query start and MySQL query done. In the start probe, let me back up, those probes execute when MySQL is about to start executing a query and also when it's about to complete executing a query. When that happens, we're running these D clauses here. In the first one, when we start a query, we grab a timestamp. That's a high-resolution timestamp. And when the query completes, we aggregate the difference between the current timestamp, which is now sometime later, subtract the one that we saved before. Don't worry if you don't understand the actual D here. The point here is kind of higher level than that. We can run this script with DTrace. DTrace will dynamically instrument the running MySQL process. And when you kill DTrace, you get the output here. This is a histogram of query latency while DTrace was running, with the number of nanoseconds on the left side. So we can see there were 1,500 queries between 65 and 131 microseconds during this interval. So with DTrace, we have unprecedented visibility into the system, basically the high-level point there. Now I want to talk a little bit about OS-level virtualization. This is another technology in Solaris. The Solaris feature is called zones. How many people here are familiar with zones in Solaris? Cool, so that's sort of a Solaris crowd here. In traditional operating systems, in traditional virtualization environments, you're virtualizing the hardware, right? So you have some hypervisor layer at the bottom of the stack, and then you have some number of virtual instances above that. And in each virtual instance, you're running a complete operating system image. So you have, if you have n virtual instances, you have n+1 schedulers, n+1 VM systems, n+1 file system implementations, n+1 networking stacks. You have all this redundancy all over the system. And additionally, the interface between the hypervisor and the individual instances is very low level, right? It's just the hardware. You know when it takes interrupts and things like that, but you don't have a good sense of higher level operations inside the operating system, like process start and done. With OS level virtualization, we basically take the equivalent to a hypervisor is what we call the global zone on a Solaris system. And there can be any number of virtual instances which are called local zones. Each local zone is not running its own kernel. As far as there's one kernel on the entire system, and as far as that's concerned, there's just a bunch of processes running on top of it. In the same way that a process might have multiple threads, a zone may have multiple processes. And the kernel uses the zone for access control and stuff like that. So each of these local zones has its own root file system. It has, you can be root there, you can do ifconfig, you see all your virtual NICs and everything like that. But there's only one kernel, which is really important for overhead. It allows us to drive our cloud to very high levels of tenancy, which in turn reduces the cost of the cloud. The other really important thing about this for cloud analytics is that from the global zone, because there's one kernel, we can actually see everything that's happening on the system. So from a single DTrace enabling in the global zone, we can see every customer's MySQL processes, for example, which means we can do cloud analytics with no additional work for each particular virtual OS instance. The customer does not have to set up any particular agent or monitoring package or anything like that. They just get it for free as soon as the zone is deployed. Switching gears a little bit, the third of these key enabling technologies I want to talk about is Node.js. How many people here have heard of Node.js? I figured that would be more. For those who don't know, it's a server-side JavaScript environment, and it's getting a lot of energy right now for a lot of different reasons. For one, for two reasons. You're able to write an HTTP server that scales to hundreds or thousands of requests per second using just that code. This is actually an HTTP server in Node that scales very well. The reason is that Node uses an asynchronous event model, which means that there's only one thread, but it never blocks. And it turns out you can actually get a lot of work done on a single CPU, on a single thread, if you're never blocking. You're always actually doing work. Since a lot of people here are familiar with Node, I'm going to skip some of the details of the example. Basically, we're just creating a server here, and that function that we pass in the middle is invoked for every request and just returns a response. Obviously, it's a very simple server. Nevertheless, it's able to scale pretty well. The other thing that makes this so interesting is that HTTP has such a first-class support in the Node library, which means it's very easy to write distributed network services using HTTP in Node, because you have everything you need right there. Speaking at a higher level, we see Node as the confluence of three ideas. One is JavaScript's existing rich support for asynchrony. JavaScript has been used for asynchronous stuff on browsers for a long time, and has supported closures and all that stuff, and developers are pretty used to that model. But we also benefit a lot from having high-performance JavaScript VMs. Specifically, Node uses the V8 VM, which is written by Google and used in Google Chrome. And Chrome is competing, among other things, on JavaScript performance with Firefox and IE. So Node gets all the benefit of this. And finally, the abstractions in Node, things like streams, are very much analogous to traditional Unix system abstractions, with which we've been writing system software for decades. So people who are familiar with writing system software have kind of a familiar environment. The asynchronous nature is a little bit different, but the abstractions are similar. The one thing I want to emphasize here is the particular case of data-intensive real-time applications, which cloud analytics is one, and a lot of other Node applications are as well. Because everything's asynchronous, the problem of latency bubbles becomes a lot more isolated. And a latency bubble is a situation where you have some operation which has really high latency, and in a traditional environment when you're using multiple threads, a thread can get blocked on that, and if the thread pool is not allocating things properly or you run out of threads, then other operations suffer as well. With Node, if one operation is slow, that operation's callback just doesn't get invoked for a while. It has no impact on other operations. This is really important for a system that wants to maintain predictable latency in the face of all kinds of failures. With these three building blocks, you can probably start to see how we're able to build a cloud analytics service. We'll start with a configuration service, which may not be clear yet why we need that, but that will be clear a little bit later. That manages the entire system. Then we have a component called an instrumenter. An instrumenter lives on each of the compute nodes in our cloud. Those are all the nodes running customer instances. It uses DTrace to gather whatever metrics data that it's been instructed to gather from the configuration service. There's one of these instrumenters per compute node, again, not per virtual OS instance. These instrumenters push data at a rate of once per second to a component called an aggregator. The aggregator combines this data from multiple compute nodes and provides that directly to clients, which can request that data over HTTP. So a picture's worth 1,000 words. We'll start with this. We have a bunch of compute nodes in our cloud. We have a big box on the left that I'm calling the data center head node, but that's actually pretty much arbitrary. The cloud analytics services live there, but they could actually live even in an instance on a compute node. It doesn't really matter where they are. And then at the top, the browser screenshot represents a client. So a user may ask us to instrument a particular thing, like say, show me the total number of system calls that all of my virtual OS instances are doing. across your cloud. That request comes to the configuration service. That's the Cloud Analytics configuration service. The first thing it does is it picks one of several aggregator services to handle that data. It verifies that thing's up and lets it know to expect data of a certain form. Then it finds out all of the compute nodes on which this particular customer has virtual OS instances running. It notifies each of them that they should be collecting this data and reporting it to the particular aggregator that it picked. The instrumenters then report data at a rate of once per second to that aggregator, and sometime later, the user's browser or API or whatever it is that's doing this is going to make requests. Those get proxied to the appropriate aggregator, and those return whatever data the user has asked for. And I say sometime later, this may be a second later, but that's how the process works. Now I want to take a deeper dive inside the instrumenter component, which is the heart of this whole system. The diagram here is kind of a slightly transformed version of the OS level virtualization one I had before. We have DTrace in the kernel at the bottom of the stack. We have the instrumenter component on the left in what is called the global zone. And then we have a bunch of virtual OS instances. At the top, we have the config service we just talked about and the aggregators. They communicate with the instrumenters via the AMQP protocol, which I'm not going to spend a lot of time on. What happens, as I mentioned, is that the config service will tell the instrumenter that it should be gathering data for some particular thing. Again, say system calls decomposed by application name. The instrumenter proper is actually a pretty generic service. It has several pluggable backends, of which one is a DTrace backend, which is what we're focusing on today. The DTrace backend uses a node module called node-libdtrace, which is a very thin wrapper around the operating system library libdtrace, which interfaces with the kernel to actually gather that data. We're going to talk about each of those in a little bit more detail. I mentioned that the instrumenter itself is a very generic service. The one thing it does specify ahead of time is which metrics the system supports. Each of several plugin modules, again, of which DTrace is one example, registers implementations of this metric. So again, take the system calls metric. The DTrace plugin says, I am able to instrument the system calls metric, and I'm able to decompose by application name. And as part of that registration, we have the register metric call there. It provides a constructor for an object. Sorry, one thing I neglected to mention is that this entire system is built with Node.js. I mentioned that was a building block, but I didn't actually point out all of this is actually Node.js, so this is JavaScript. Again, when the instrumenter starts up, goes through the plugins, asks them to register what metrics they know how to implement. The DTrace backend will register that it knows how to implement, say, the syscalls metric, and provide a constructor for an object which will actually implement that. And the interface for that object is actually pretty simple. When the instrumenter receives a request to instrument this thing, it uses the constructor to create this object, invokes the instrument method, which will generate a dscript and go actually enable DTrace. And then it will call the value method once per second to actually retrieve the data. When that's done, it'll call the dinstrument method to clean that up. Again, let's take a look at that in a little bit more detail. When the DTrace backend is asked to instrument a particular metric, the first thing it has to do is generate a dscript that will actually go get that information from DTrace. That part is a little bit more complicated, and I'll get into that in a sec. Once we have that, it's actually pretty straightforward. These lines of code are almost lifted from that file. It basically just passes that script over to DTrace, and it calls a function called go, which tells DTrace to go enable this thing, and then we can start gathering that data once per second. The question, though, is there are actually a large number of different related metrics that we might be interested in. So the one I described is just system calls. This is a very simple dscript. When this call returns, we just keep a counter of how many times that happened, and we check that. Now suppose the user asks us to decompose this by application name and latency, say, because we're generating a colored heat map like Brendan showed before. This is a very similar script, but obviously it's a lot more complicated. On the entry probe, we gather a timestamp. On the return probe, we quantize on the difference between the timestamp and the latency that we gathered before. Sorry. We quantize on the difference between the current timestamp and the one that we saved before. And we key that in an aggregation key by exec name, which is the application name. These two scripts obviously are from the same family of things. You could think of the first one as a much simpler version of the second one. But they're basically implementing the same thing. And when you consider that we want to support easily a dozen different fields like application name, process identifier, parent process identifier, etc., the number of such scripts grows pretty large. So you need a way to automatically generate these things. So we invented I don't want to call it a language, it's almost a syntax, a JSON-like way to represent a family of dscripts that differ in the way you can decompose, in the fields that you decompose by, and also predicates that you can apply. So for example, the predicates allow you to filter data. So you can say, I only want information from application name MySQL. Again, metadata is one of those things we could spend a long time on, so I just want to go over some of the basics here. The very top line, if you can read it, basically just says, this is the metric that we're instrumenting, namely system calls, and we can decompose by host name, zone name, application name, and latency. Then we have a list of probe descriptions. In each probe description, we say what information we might be gathering. In the first one, we have the syscall entry probe. We're gathering a timestamp, and we're doing that only when we need to gather the latency field. In the second description here, that happens on syscall return. We describe how we're going to count the total number of things for this particular field. If we're decomposing by exec name or anything like that, in most cases it's very simple, we're just keeping a count. For something like latency, where we want a heat map, then you actually need to quantize that. Instead of saying, I'm just going to count for each exec name how many we saw, for latency we actually have buckets. So we say if this is between 0 and 100 milliseconds, then that's one bucket. 100 to 200 milliseconds might be another bucket. The LL quantize there is a log linear quantize, and the parameters just describe what that curve actually looks like. The details aren't that important for this. So now we've generated this dscript, and we've handed it off to DTrace, but how does the magic actually happen? In the system calls case, it's relatively easy, although maybe not obvious. Again, remember we want a system with zero disabled probe effect, which is absolutely safe in production. That's the whole point of this thing. Well, the way kernel system calls work is each system call has a particular identifier, just an integer, which indicates which syscall it is, and there's some function which implements that. Inside the kernel, there's a table that maps these integers to the function that implements that. When you enable tracing for a particular system call, DTrace atomically changes the pointer for the implementation of that system call to a function inside the DTrace module, which fires whatever probes the user has asked it to fire, which just gathers whatever information it asked it to gather, and then executes the body of the system call, and then fires whatever return probes are appropriate. Remember, each of these probes is doing something very quick. It's like gathering a timestamp, right? This is a very lightweight operation. Important pieces here are that there's zero disabled probe effect, because when DTrace is not enabled, the system calls are running as normal. And there's minimal effect when enabled, because we're just calling a different kernel function, which is gathering additional information. At no point is the thread stopped. So in a traditional environment like truss or strace or something like that, you actually set breakpoints at the system call points, and the process actually stops, goes over to the tracing program, prints something out, and then resumes the process. That's much more invasive from a performance point of view, and it's not always totally safe. The other advantage of this approach is that we're instrumenting all of the system calls on the system at once, whereas with the previous approach, you would actually have to go to each application you think you might need to instrument and do it individually. Let's look at a slightly more complicated case. Instrumenting MySQL. This script here looks a lot like the system call script we just looked at, except instead of syscall start and done, this is MySQL command start and done. Again, at the start probe, we gather a timestamp. At the done probe, we quantize based on the elapsed time and keyed by the command name. By this point, this should be a pretty familiar example. How does that actually work? It looks a lot like the system calls one, but obviously we can't just change some pointer in the kernel and start gathering this data. It uses something called userland statically defined tracing in DTrace. This represents probes that are statically defined by developers in an application like MySQL. So in this case, the MySQL developers have actually added code to support DTrace using special macros that DTrace provides. The reason we do that, by the way, is because DTrace is actually capable of instrumenting individual instructions in the process as well as function entry and exit, and you could build a cloud analytics system based on that. The problem with that is if you were instrumenting multiple different MySQL versions, for example, functions change names. You don't really want to rely on function names as a stable interface. By using static probe points in the application, you're protected against changes to the source base. You know that this point in the code is the actual semantic point where a query starts or finishes. It doesn't just happen to be for this particular version. Anyway, with USDT, the way it works is in the source, you actually put a DTrace macro. This macro expands to a special DTrace function call. But that function doesn't actually exist anywhere. During the link phase, the references to this function are replaced with a sequence of NOPs. These are no-op instructions that the processor will ignore. However, the locations of all of these things are recorded in the binary. Later, when you go enable DTrace, DTrace finds all the locations where this probe was fired by looking for those references to that function call, replaces the NOPs with an instruction which will trap into the kernel. So when the application is running normally, we have the zero disabled probe effect. The application runs right through this code. There's a bunch of NOPs, which is actually not measurable. Brendan tried to measure it, and you actually can't see that. When you go enable DTrace, you hot patch the text to trap into the kernel. The kernel fires whatever probes it needs to, and then immediately returns back. It's a fast trap, so it doesn't do all the stuff that the kernel would do for a normal system call. Again, the thread is never actually stopped. It does take a round trip to the kernel. We have zero disabled probe effect. I've already mentioned the PID provider and why we're not using that. Just to kind of sum up some of the DTrace key points here, we can actually combine userland and kernel tracing in the same DTrace enabling. So for example, we can tell you not only HTTP request latency, and not just CPU dispatcher queue latency, but how much time during a particular HTTP request was spent, say, waiting on the thread dispatcher queue, which is pretty important in the cloud where you have a multi-tenant system and CPUs may be a bottleneck resource. So you can actually tell, am I being kept off CPU because other customers or other instances are on CPU? Similarly, we can tell you how much of MySQL query latency is directly attributable to file system latency. We can do this for all applications at once, as we talked about, and with cloud analytics, we can do this for all systems in the data center. So we can actually show you a heat map of, say, MySQL query latency for all of your MySQL instances in a single data center. I've talked to death about zero performance impact, non-enabled, etc. The last thing I want to talk about briefly are the visualizations, which is the important part. At the end, the user actually wants to be able to make sense of this thing. The aggregators I mentioned earlier store the raw data on a per second basis. There are a lot of client libraries which can draw a line graph or bar charts from a set of data points like that. We used Flot for a while, we've switched to using D3, and that's not necessarily that hard a problem. I mean, it is a hard problem, but we're picking an off-the-shelf component for that. What's a little bit harder are these heat maps. Heat maps contain a lot of raw data, actually a lot more than, say, a bar chart. And in fact, if you think about it, the most compact representation of the heat map is the ping image itself, where you just have basically one byte per bucket in the heat map saying how much stuff was there. So rather than transferring all this data back and forth, we transfer this data, we render the heat map on the server side, and we transfer that. Remember, we're doing this entire thing in Node, and Node is single-threaded. So if it takes, say, 100 milliseconds to render a heat map, that puts a pretty finite upper bound on how many requests per second you can serve. Actually, it's more like 10 milliseconds for a heat map. Requests can take up to 40 milliseconds because we have to massage the data before we do that. But we still need multiple aggregators in order to do this. So that's why we had that fleet of aggregators at the beginning, and that's how we parallelize this. So one of the problems with Node is traditionally that it's hard to parallelize computation. In our case, it's actually really easy. When someone creates a new instrumentation, as I mentioned earlier, we pick an aggregator to put that one on, and that's where the data will live on that's where the data will live for all of the data for that instrumentation. We just need to make sure we load balance these across aggregators and have enough aggregators that we can fill the CPU, because the aggregator is what's actually going to be generating a heat map. Here's a diagram of what I was just describing. The client requests come in over HTTP. They actually go through the configuration service, which knows which aggregator it's actually on. And then it goes into the appropriate aggregator and either gets back raw data or goes through one of a couple of different components to generate a heat map. Then I want to switch over to the demo.
So we've set up a demo. If you can point your browser, and I'll go through it very quickly. If you can point your browsers to rm.nl.de 8001, and I'll just switch the screen. So this is a Node.js program that we can show what the heat maps look like live and go through some of the instrumentations. So Dave's just getting that set up now. We're doing this in production on a part of the Joyent cloud called init.de. The first view that you see here is, that should be fine. The first view that you see here is a global view, except the colors are washed out on this display here. What you can see is there is a world map here. There's an outlines feature, this projector. And Dave's just clicked on a point which shows there, which is the US of A is here. So that's New York. So when you first log into Cloud Analytics, we just give you a summary of what your entire cloud is doing, superimposed over a world map with geographic data, so that you can see as traffic moves around. Sorry, we should stretch the colors to make the world map actually visible, but someone's just logged in from 174.253.196.71, which must be Colorado, if that's New York. And if other people log in, you'll see where they're coming in there. That's just the overview, but I'll get Dave to click on Analytics, where we do the drill downs in detail. And listing the instrumentations, we've got a set of, this is the first generation of our Cloud Analytics software, where we only had about 5. We've got some Node.js instrumentation, file system, and CPU thread executions. On the very latest version, there's about 25 of these. Now that Dave's done all and the team have done all the engineering effort that he just described to make this possible. And I'll go to HTTP server operations decomposed by latency and then URL. And it'll come up pretty quickly. What's happening is this is where DTrace is going and live patching the Node.js userland process and changing those knobs into the actual instrumentation. And this is the heat map of this one is showing the HTTP server operations by latency and URL. And this is the primary measure of your performance for the application. If it's a Node.js application, this is showing how long does it take for my application to respond to clients. The higher it is, the worse it is. And as we can see, there's a couple of different characteristics of the latency here. And if Dave clicks on, this is the actual URL, it just happens to be a random unique identifier, we can map how different URLs on our application are getting handled. This is just a dummy test program, but for a real application, this would list the various interfaces, and you could actually make a live change to your software, the developers could, and you could see immediately, is my latency getting worse? Do I have outliers up the top? Has latency gotten better? Without losing information because you're doing it via a line graph or anything else. And again, this is the entire cloud, so even if you've got 1,000 nodes, they'll all be displayed here. Another type of breakdown we can do for the same instrumentation, instead of URL, we can go to the remote IP address. And let's create that now. And the remote IP address is, I was hoping this would be more interesting, but I think we're all going through this particular proxy. But you can quickly get that data to find out if any of your users have a particular latency issue. In fact, Dave's doing a great demonstration of errors, so the sort of bugs that we fixed since the first generation of this software. Let's bring that back up again. That's the HTTP server operations. A couple of the other breakdowns to show quickly include, let's bring up, there is garbage collection operations which we can do by latency, but this is Node.js is not doing much garbage collect at the moment. There is also HTTP client operations, which we can bring up by latency, though this application is not doing it. That's interesting because many applications will go and do things to other services like Twitter or Facebook, and you can bring up the latency of those requests and then compare them to the delivered latency of your application. For an example of this, let's bring up the file system, logical file system operations by latency and operation type. Now, I've seen a lot of monitoring environments that are trying to understand file system performance using disk-based metrics. That's really hard to do. Disk I/O, the sort of metrics you build on top of I/O stat, are at the bottom of the stack, and you have an entire file system and caching in between with asynchronous threads like read ahead and prefetch. What we did was we instrumented the top of the file system so that we can see the actual delivered latency to the application. Tools like DTrace makes it very easy for us to do this because we can just say, show us the latency for the VFS interface into, say, ZFS or whatever it is. And this is showing latency of file system requests. I'm running a deliberate workload that injects some I/O that have a known latency, or close enough that's spelling out OSCon. So it took me far too long to write that program. We can also break this down by things like offset and size, which is very easy to construct because that's the parameters of your program. To actually write a workload that injects a stream of I/O that has a known latency is actually much harder. So it's kind of impressive if you understand the details. So that's my program that I'm running. Those are reads, and we can click on these things at the bottom and to identify what they are. And so clicking on the pixel shows that that's. You can click on it. There's lookups and readers. Having this on the screen at the same time as the top level performance, which was the node, the delivered latency, is hugely useful because we can compare. This is what matters. This is what the application is delivering. And we can then go and generate these heat maps for all sorts of other areas. So garbage collect, say those Twitter calls, say the file system latency, another one there was CPU runtime latency. And then you can compare the latency patterns here with your eyeballs with the delivered performance. If you know DTrace really well, you can write that DTrace script that joins together the data. It's very hard to do. I read the DTrace toolkit. It's something that would take me a while to do to associate all the different layers of the operating system stack up into application context. So we're kind of cheating. We're using our eyeballs to do it by looking at the latency at different levels, and we can, if you see a particular cloud of latency, and the resolution here is very beneficial because you can then pattern match with the delivered latency. So if I saw the word OSCon spelled out in the Node.js performance, then I would know it's due to the file system. Like, I don't need to write the script that actually connects those layers together. I could, DTrace lets me do that, but we're using vision pattern recognition to make it much easier. So of course, each time we're opening these things up, it's creating DTrace scripts to do the instrumentation. And the last one I'll open up is the CPU. We'll do CPU thread executions by time on CPU and application name. And this shows us, there's all sorts of different ways you can present CPU utilization, but this one is showing when you go on CPU to do some work, the latency is the time you spent on CPU. So if you changed your application code and it happened to be on CPU for longer, that pattern would stretch upwards. And again, you can pattern match that versus the application layer to find out where the application is responsible. This is actually really useful, really exciting stuff for the customers I'm working with. The primary question they're asking of their cloud apps is, I know I have a performance problem. What team solves it? Do I give it to the sysadmins? Do I give it to the DBAs? Do I give it to the web developers? Who do I give that to? So with cloud analytics, we can look at the pain in detail, the heat map of the delivered latency, and then if it matches the file system heat map, it goes to the sysadmins because they're responsible for the file system. If it matches the CPU heat map, it goes to the DBAs because you're on CPU doing MySQL code or Node.js. If it's MySQL, then it'll be the DBAs. If it was Node.js, it would be the developers of that. And we've added many other breakdowns from all around the OS so that the businesses can make that very first determination, which is hugely useful. Which team works this issue next? And then we can drill down further and get more information on it. In fact, this one's pretty. We've got Node is up here, latency library, which is my dummy tool, is faster, and my SQLD is on the scene as well. So that's latency-based metrics, and we're finding it very useful and practical to solve problems that previously had spent weeks of looking at sort of unrelated data that the operating system gave you. We're generating these latency-based metrics. And with DTrace, we have the ability to invent new kernel-based metrics, say dispatcher queue latency, the file system latency, and since we're working on the Lumos, we're also adding new metrics back to the kernel to generate these heat maps. So, yeah. So that's a quick demo, and Dave's just got a final couple of slides with references.
We kind of, I think we covered most of the stuff that I was going to talk about. I mentioned that this is all written in Node.js. Specifically, it's about 85% JavaScript and 15% C++ by lines of code. Obviously, it's a little bit not representative. It's almost entirely JavaScript. Talked about parallelization. Do we have a screenshot?
That's what I was trying to do.
That's it. Thank you, guys.